Okay, welcome back, students. So today I just have prepared one final exam for you. It is actually a final exam prepared on Applied Mathematics 3 course. So I just have brought for you right now just to understand how the exam looks like. And in addition to that, you are supposed to again recall what you studied in your semester course under this Applied Mathematics 3. So I just have prepared this for you in order to make your study fruitful. So as usual, I just need your subscription. Let me just directly go to the final exam. As can be shown here, the final exam is given for 3 hours, and it has actually 7 pages, but I just have tried to condense it. Anyway, this is these are the exam is going to have two parts. One is instruction one part, and that is the fill in the blank part, and the other is the workout part. So in the fill in the blank part there are 10 different questions, as you see. So we are going to see how we can find the solution of these. And when you come to the workout part, you see the workout part is having actually 5 different kinds of questions from the contents of the course. So I'm going to show you again how this can also be done. So as I said earlier, your subscription is very important because I'm just preparing this for you in order to support different students. So you need to like, subscribe, and inform other students for their successfulness. Now when I directly go to the first question, it says if f of t is given by cos t sine hyperbolic t, then you are asked to find the Laplace transform of this function. So the Laplace transform of this function can be obtained as follows. As you see, the function f of t is given by cos t sine hyperbolic t. But as we know, sine hyperbolic t is defined as e to the power of t minus e to the power of negative t divided by 2. And from this, what you need to do is you have to recall shifting property. Because I'm going to take this 1 over 2 out and then take cos t with et as well as cos t with e to the power of minus t. And then I will try to apply shifting property to find the final output. So as can be shown here, look, this is 1 over 2. Now this 1 over 2 is taken out, so cos t times e to the power of t minus e to the power of minus t cos t can come. I just simply multiplied cos t for each of these two. Now what comes next is this one. So you are asked to find Laplace of this function, so have Laplace both sides, Laplace of the function f of t, and here you are having 1 over 2 and have Laplace for these two. Laplace of e to the power of t cos t minus e to the power of minus t cos t. Laplace undergo linearity property, so the Laplace of the difference of two functions is the difference of their Laplaces. Therefore, this is going to be 1 over 2 Laplace of e to the power of t cos t minus Laplace of e to the power of minus t cos t. So from the shifting property of Laplace, basically this is going to be the following one. We know that the Laplace of cos t is s over s squared plus 1, but here we are having 1 as a coefficient of t. Look, as a coefficient of t we are having 1. So using shifting property, in place of s of this Laplace transform for cos t, we're going to put s minus 1, right? S minus 1 is going to be used. Here the coefficient of t is negative 1, so in place of s of this Laplace transform cos t, which actually is s over s squared plus 1, we need to put s plus 1 because we are having here minus. So recall that the Laplace of e to the power of at times f of t is the Laplace of it is going to be the Laplace of f of a minus t. So we need to recall that one, and we will use the shifting property in order to determine the result. So from this we can have the following one. As you see, 1 over 2 comes as it is, and then look here, the Laplace of cos t is known, and that is s over 1 plus s squared, but in s you need to put s minus a, where your a is here 1 because the coefficient of t is 1, so s minus 1 is going to be used in s. Okay, it was actually s over 1 plus s squared, but now s minus 1 is used in s. The same is done here. In the case of cos t, we do have s over 1 plus s plus 1 squared, but this is s minus a. In s, we need to use s minus a. Your a is negative 1 here, so s minus minus 1 comes s plus 1. So s plus 1 over 1 plus s plus 1, the whole squared can come. So if you want to simplify, you can further simplify it, but actually the answer is going to be like this, as you see. Now going to the second question. The second question is going to be this one. You are given f of s to be like this, 6s minus 2 over s squared plus s minus 6. Now you are asked to find the Laplace inverse of f of s. Mind you that we are supposed to answer our blank space in terms of t. This is talking about Laplace inverse transform. So actually for this we need to remember the composition of this rational expression. So the solution for this goes as follows. Here it is. The Laplace inverse of f of s is the Laplace inverse of this one. What I did here is I just simply introduced Laplace inverse both sides here at the same time the right side too. Now here you need to undergo decomposition for this particular expression. So Laplace inverse of a over s plus 3 plus b over s minus 2 comes. The reason I'm having here s plus 3 and s minus 2 is I simply decomposed this. I just have taken two numbers where their sum can be positive 1 as you see and product negative 6. Remember the factorization of quadratic expression, and I obtained the two to be 3 and minus 2. That's why I'm having here s plus 3 and s minus 2. So these two are linears, and so we need to have constants as numerators here, a and b. Now let's look for values of a and b so that you can have 6s minus 2 there. So this is going to be Laplace inverse of, look, as you are decomposing this, you are going to obtain a to be 4 and b to be 2. Basically, here students, decomposing this is very simple. What you need to do is, you see, multiple a by s minus 2 and again b by s plus 3. In doing so, you will obtain this to be a plus b times s and 3 minus 2a plus 3b. And the coefficient of s must agree with 6, it must match with 6, and the constants 3b minus 2a must match with minus 2. And so you are going to encounter systems of equations with two unknowns. So you are supposed to find these values a and b from that. So as you are doing that, you will obtain a to be 4 and b to be 2. Now Laplace inverse undergoes linearity property again. So the Laplace inverse of the sum of these two functions is nothing but it is the sum of the Laplace inverse of each of these two. So this is going to be equivalent to this one, as you see, the Laplace inverse of 4 over s plus 3 plus Laplace inverse of 2 over s minus 2. So as can be shown here, 4 can be taken out, and Laplace inverse of 1 over s plus 3 is a power of minus 3t. And the Laplace inverse of, you see, 1 over s minus 2 is a power of 2t. So 2 is taken in front, so it will be like this. So dear students, it is a Laplace of this that makes this expression the one given here. So the Laplace inverse can be obtained in such a way. Having this into account, what comes next is the question, the third question. So this again requires the second Laplace, the second shifting property of Laplace transformation. You are given a function g of t defined in a piecewise manner, as you see. For t greater than 2, you have been told that g of t is t minus 2 cubed, and for t less than 2, it is 0. So you are asked now to find the Laplace transform of g of t. Now, students, you need to recall about the Laplace second shifting property. So using that, we can find the answer for this one. So remember that in the case of this kind of definition, Laplace transform of g of t is e to the power of minus as times Laplace transform of f of t. And how is f of t noted? F of t is t cubed. You see, students, f of t is t cubed, and this t cubed is directly taken from this expression, okay? It is t minus 2 cubed. Actually, we were having t cubed, but inside t, we are having now t minus 2. So in case your function is defined this way, you see, we need to use second shifting property of Laplace transformation, and that is the Laplace transform of this function is e is a power of minus a. So what is a? A is nothing but it is 2 in the case of this, because the value that makes the expression inside the bracket 0 is 2. So your a is 2. And your f of t is t cube here, student, t cube here, because in t we are having t minus 2. So the Laplace transform of g of t is e to the power of minus ac times Laplace transform of f of t, given that f of t is t cubed. So from this directly we can add this one. Your a is, as I told you, 2, and f of t is t cubed. So from this, what comes next is Laplace transform of power function must be recalled, and that is 3 factorial. This is a power of 4 because we are having 3 here, so Laplace of t to the power of n is n factorial over s to the power of n plus 1. Since n is 3, we do have 3 factorial divided by s to the power of 4. We knew that 3 factorial is 6, so this Laplace transform is going to be 6 over s to the power of 4 times e to the power of minus 2s. So dear students, as you understand from this, you need to recall the Laplace definition as well as you see properties of Laplace in order to solve different kinds of Laplace questions, right? Okay, dear students, now comes question number 4. The directional derivative of the function x squared y z squared in the direction of u I plus j plus k at 1 to 1 is blank. So here you need to recall the concept of this directional derivative. So let you see how I'm going to do this. So first we need to change the given non-zero unit vector to unit vector, and this is a vector given which is u I plus j plus k. This is not a unit vector because its magnitude is radical 3, because square root of 1 square plus 1 square plus 1 square makes what? Radical 3, so it's not unit. So to change a non-zero non-unit vector to unit vector, we need to divide the vector by its magnitude, as you know, and we need to have that one because it is a unit vector that has to be considered in our formula. So u is I plus j plus k, so we need to divide this by its normal, and this is 1 over radical 3 I plus j plus k. Now it turns to be unit vector 4. And first, next we need to determine the gradient of this function. So the gradient of this function is the partial derivative of f with respect to x along I, partial derivative of respect to I along j, and partial derivative of respect to z along k. So this is going to be this one. We just simply take the partial derivative with respect to x, which actually is 2x y z squared, as I wrote. And with respect to y, x squared with x squared z squared can come, and with respect to z, 2x squared y z can come, right? So these partial derivatives represents, okay, the gradient of the function. So now the next thing is we have to evaluate this gradient at the given point. So when you are taking x1, y2, and z1 here in place of fx, fy, fz, we can obtain this value to be 4i plus j plus 4k, as you see, right? 4i plus j plus 4k. So when we come to the meaning of this directional derivative of the function, it is the dot product of the gradient of the function at that particular point times, the dot with the unit vector, right? The unit vector u, as you see here. But we already determined what the gradient of f is. It is 4i plus j plus 4k. So unit vector u is 1 over radical 3 I plus j plus k. It's directly taken from this one. So this now can be done like this: 4 times 1 over radical 3 is 4 over radical 3, and 1 times 1 over radical 3 is 1 over radical 3, and 4 times 1 over radical 3 is going to come because this 1 over radical 3 is going to multiply each of these. And then, as can be shown, 4 over radical 3, 1 over radical 3 plus 4 over radical 3 is going to be obtained. So the slope of the tangent line you see to the surface in the direction of the given vector is going to be, at this particular point, is going to be 9 over radical 3. If you want, you can rationalize this Otherwise, this can also be taken as it is. So when you rationalize this one, it will be 3 radical 3. So the directional derivative of the function at the particular point 1 to 1 in the direction of the given vector is going to be this much. Now comes the next question, and that is the fifth one, and it says you are asked to find the particular solution of this one. In fact, this is a second order non-homogeneous differential equations with constant coefficients. So here we need to find the homogeneous solutions and particular solution, and then we'll take the sum of the two finally. So the solution proceeds in this way. The characteristic equation for the homogeneous one is m squared minus 6m plus 8 equals 0, because as you see, just consider m to be in y, so m and the order of the derivative is considered as exponent here. So m squared minus 6m plus 8m the power of 0, because no derivative here, 8m the power of 0 is 8, is equal to 0, because now we are considering the homogeneous one. So from this, if you remember, this can be factored as m minus 4 and m minus 2, because we were thinking of two numbers where the sum is minus 6, product 8. Now from this, one can get m to be 4 or m to be 2. So the homogeneous solution is going to be c1 e to the power of 40 plus c2 times e to the power of 2t. Look here, student, that the homogeneous solution is having two constants c1 and c2, and these are basically arbitrary constant numbers, real numbers. Okay, now we need to find the particular solution, because this is not the homogeneous one, it's not 0 as you see. So we need to think of an expression where we can have this yp to be. So for that, look, this is written in terms of exponential form, so we need to take a here because this is a constant one, and e is a power of t because it's a coefficient of t1 is not the root for this homogeneous differential equation, but had it been a root we could have considered extra t in front. But for the time being, let we take this to be a times e to the power of t. So the derivative of this is going to be a times e to the power of t. Again, the second derivative of this is this one. I'm taking yp to be in this form because you see I'm claiming here that the particular solution is of this kind. So yp's first prime and yp second derivative all are obtained, so I cannot directly put this second derivative result here in my equation, and the first derivative result here also, and you see my yp to be here, so that I can adjust this in order to be q equal to 2 times e to the power of t. In doing so, I can determine what is going to be. So this was, you see, my question I was having here. So just substituting the expressions here, I can have a times e to the power of t minus 6a e to the power of t minus 8a to the power of t. So this has to be equalized with 2 times e to the power of t, because you have been told that this must make to e to the power of t. But I know that 1 minus 6 makes minus 5, and minus 5 with a minus 8 makes minus 13. So negative 13 times a e to the power of t equals to e to the power of t. So I can cancel now e to the power of t by e to the power of t. Now I'm left with a minus t over 13. So the value of a is now known. So if I am able to know what a is, I can directly substitute that here and know what my yp is. So my yp is going to be minus 2 over 13 times e to the power of t. So the particular solution is going to be the y homogeneous plus y particular. I mean, this is a general solution, students. This is a general solution. Actually, yeah, this says a particular, but make it general, students. General solution, okay? So the general solution is going to be the sum of the two. So c1 e to the power of 40 plus c2 e to the power of 2t minus t over 13 e to the power of t. So if you are asked to find the particular solution, in fact, you can put a to be negative 2 over 13 e to the power of t. It's possible to put that here. But if the question is, you see, to ask you a general solution, you are supposed to write this. But for the time being, even if I am just I just have solved everything here, The question says a particular solution, so you are supposed to write this unknown, okay? Negative 2 over 13 is a power of t. Negatives 2 over 13 is a power of t, but had it been a general solution, you see, we could have written this one. I hope you have understood it. Now, having this into account, what comes next is question number 6. This question says find the value of k for which this given differential equation can be exact, right? So basically there is equal 0 here, students, equal 0 here, it's forgotten, but we must have that one. So your m is x cubed y is the power of k, and your n is 1 over 2 y x is the power of 4. So the solution goes like this: your m is x cubed y is the power of k, and from this the partial derivative of m with respect to y will be, as can be shown, this y is the power of k. When k comes down, it will be k x cubed y is the power of k minus 1. This is how the partial derivative of m with respect to y is going to be obtained. And your n of xy is the coefficient of dy, which actually is 1 over 2 yx is the power of 4. So your n of xy, as you see, is 1 over 2 yx is the power of 4. So the partial derivative of n with respect to x is nothing but it is, you need to bring 4 down in 4 over 2, which actually is 2. Y is kept as it is, and deduct 1 from 4, you will have cube here, x cubed, so this is going to be 2x cubed y. But remember that a differential equation which actually is exact must satisfy the condition that my equals nx. So my equals nx implied that, look, this is your my and this is your nx, so we can cancel x cubed by x cubed. In order to make it for general, x must be different from 0. So ky is a power of k minus 1 equals 2 times y can come. So the value of k can easily be directly obtained from this one. It is 2, and it agrees with all, again, these 2, because 2 minus 1 is 1. So even if it's not written, the exponent here is 1, 2. So the value of k is going to be 2, as you see. So for this differential equation to be exact, necessarily the value of k must be 2. Okay, students, now comes question number 7. You are given with a vector function f of x, y, z to be xi plus yj plus zk, and the curve here is C, which actually is a circle with center 0 and 2, because this is x squared plus y minus 2 the whole squared, and its radius is 3 because the square root of 9 is 3. Then you are asked to find the line integral of this vector function over the curve. So this recalls how you can carry out line integral of a vector function over a certain curve, in our case a circle. So basically this is done in 2 different ways. So I'm now going to show you how this can be done by using first approach, and next I will tell you a shortcut technique how you can obtain solution of this kind of question. So when I directly go to the solution part, you see this is going to be like this. As you know, dear students, whenever you want to find the line integral of different function, it could be scalar or a vector function, what you need to do is you have to know the parametric vector equation of the curve, because as we know, the line integral is defined on that particular parametric vector form. So as you know, this is a circle with center at 0, 2, and the radius, 3. And if you remember, students, every circle with a radius 3 has making its center at the origin has an equation of r of t is equal to 3 cos ti plus 3 sin tj. And here, look, 3 cos ti plus 3 sin tj represents the equation of see a parametric equation of a circle with center at the origin in the radius 3 unit. But now the center is moved. See, the center is moved to 0 and 2 because 2 minus 2 makes 0. So the center has shifted from the origin to 0 to 2. So we need to use translation property. So if the center moves from 0, 0 to 3, 2, again the parametric equation changes, and the parametric equation is nothing but it is adding 0 and 2 on 3 cos t and 3 sin t respectively. So you will finally come across with the parametric equation of this circle to be 3 cos ti, because 0 plus 3 cos t, 0 is 3 cos ti, and the 2 plus 3 cos 3 sin t is going to be 2 plus 3 sin t along the j component. So for one complete revolution of a circle, our t runs from 0 to 2 pi. So this is going to be the parametric equation of the circle given by x squared plus y minus 2 the whole square equals 9 for t running from 0 to 2, but 2 pi. Once we have this, now what comes next is the assignment. So here x is your 3 cos t, because as you see the x component of your parametric equation is 3 cos ti. So the x is going to be 3 cos t, so directly you can know what dx is. The change on x is going to be minus 3 sin ti, it's minus 3 sin t dt. And if y is going to be 2 plus 3 sin t, and the derivative of this with respect to y with respect to t is going to be dy is equal to 3 cos t dt, because this one is a constant one, it will be 0. So the derivative of 3 sin t is 3 cos t dt. So dear students, every variable is now written in terms of t. So later when I use this expression and write in terms of t, everything can be obtained. This the integral of f dot dr is going to be like this, as it has been given here. Your f is xi plus yj plus zk. So I just directly took this one and wrote it here. You see, n dot what is dr? Dr is dxi plus dyj plus dzk, because we are in 3 axes xyz, so we need to have dr to be dxi plus dyj plus dzk. So this integration is going to be, you see, the integral of dot product of two vectors, which actually is this one. What I did here is just simply substituted what x is 3 cos t, and y here is 2 plus 3 sin t, and your z is we don't have z component here, right? Yeah, it's good. So if you don't have the z component here, you see, we will consider that to be 0k, right? 0k, because the z component here is, you see, what is that, j, and what was that? Yeah, this is totally given in terms of, it is given on xy plane, so we don't have k component here, it is 0. So you do have here 0k, so I'm not going to write that. Dot row is, what is dx, students? Dx is nothing, but it's the one obtained here, minus 3 sin t dti. And what is dy? It's already done, 3 cos t dtj. Since z is 0, dz is going to be 0, so we are left with this. So everything is written in terms of t, so we need to write t's interval. So our t runs from 0 to 2 pi, so this here we have 0 to 2 pi. So how are you going to do this dot product? So remember how we can carry out dot product into vectors. So this is 3 cos t, it will multiple minus 3 sin t, and it will be minus 9 cos t sin t. And this must multiple this, 2 times 3, 6 cos t, and 3 sin t, 3 cos t makes 9 cos t sin t. So altogether we do have this one. Look, if you observe this first expression and the third one, you see one is the negative of to the other. So one can cancel the other, and then we can have the integral from 0 to 2 pi of 6 cos t dt. So can we take 6 as a common out? Yes, and then sin t can come, but as you are substituting 2 pi and 0, 1 after the other in place of sine, this comes to be 0 minus 0, and it will be 0. You see, student? So this is the first technique that we can do. And when we come to see the other concept, you need to recall this one. Remember, students, we studied this. If f here, capital F, the vector 1 is the gradient of a certain scalar function, we call this function, the vector function f, conservative field. So clearly f is conservative because it is the gradient of a scalar function, this one. Basically this is f of xyz, student, f of xyz, okay? Please correct that by that. A function of 3 variables, scalar function, 1 over 2 x squared plus y squared plus z squared. So if you carry out gradient of this one, you will finally come across with this. So if capital F behaves this kind of property, if capital F is scalar gradient of a certain scalar function. The scalar function is called the potential function, and the one taken here as a vector is considered to be the conservative field. So if f is conservative field, students, then it is path independent. That is to say that it doesn't depend on the path we are moving from the initial to the terminal one. Instead, it depends on the initial and terminal points. Since we are having a circle here, you see the initial point and the terminal point coincides. So this is going to be, you see, this value at, this value at the end point minus this value at the initial point. Since the initial and the terminal points are identical, and since we are also having same function, the result comes 0. So you need to know, student, that if f is conservative field of a certain scalar function, the integration is called a path independent. And moreover, since again the curve is a closed one, the path independent integral goes to 0. It has to be noted. So after having this, what comes next is another question, and this is the 8th question. You are asked to find the work done by a certain force given by 3y to x 4z that moves a certain particle along the curve C from 0 to 1 of t value by this position vector r of t. So let's calculate that in terms of joule. Assume that this is given in terms of Newton and this is given in terms of meter. So in a way, this is obtained in the following way. Your r of t is ti plus tj plus tk, and t runs from 0 to 1. So from this, your x is t. Clearly, your x is t. So the derivative of x is dt. You do have also dy to be what? Dt, because y is t, and the same is true for this. dz is dt because z is t. So from this, what follows is the integral of f dot dr is going to be 3yi plus 2xj plus 4zk, directly taken from this one. Dot with dr is dxi plus dyj plus dzk. So having this what's called dot product, we can have 3ti plus 2tj plus 4tk, dti plus dtj plus dtk. So carrying out this integration, you do have 0 to 1 because t is running from 0 to 1 as I wrote over here. Then 3t, 2t plus 4t can come, just applying this dot product, and finally this makes, actually I can also add this, 3t plus 2t plus 4t makes 9t, and 90 squared over 2 can come, and as you are substituting these values, 9 over 2 can come, but I can also perform the integration for each of these. But as I said earlier, this is integral of 90. So 90 squared over 2 can come, and as you are substituting 1 and 0 one by one, you will encounter 9 over 2 as a final output. So if this force is given in terms of Newton and if this is given in terms of meter, this much amount of joule is going to be done by the force in order to, just by doing a certain work. Okay, dear students, now proceeding to the next question, question number 9. Here we have a certain line integral questions again. If C is the boundary of the region bounded by y is equal to x and y is equal to x squared, then you are asked to find the line integral of this vector function xy plus y squared along I and x squared along j. Basically, dear students, this just recalls the concept of what's called Green's theorem, because considering these two different functions, y is equal to x and y equals x squared, you are supposed to have a certain bounded region. So whenever you have a sentence that says boundary of the region, you need to recall that concept, Green's theorem concept. So using this Green's theorem concept, we are going to find the line integral of this one. So this is how it can be done. So here it is, using Green's theorem, we do have this one, the line integral of m dx plus m dy is equal to the double integral of nx minus my dA over a certain region, or so Green's theorem associates line integral with double integral, as can be shown. So what you need to do is you have to identify the I component of your vector here, see, and the j component of your vector, because the I component is considered as m and the j component is considered as n, or try to take m to be the one before dx. So this is your m, as you see, and the one before dy is considered to be n, so your n is going to be x squared. So since these two make a certain closed and bounded region, the integral of this vector function over this closed bounded region having anti-clockwise or counterclockwise orientation is the same as this double integral of the partial derivative of n with respect to x minus the partial derivative of n with respect to y over what? The enclosed region, okay? This is the idea of this Green's theorem. So your m is, as I said, directly taken from this one. It is xy plus y squared, and from this you are supposed to calculate what my is because it's used here. So we need to find my. So my is a partial derivative of m with respect to y, so it's going to be x plus 2y, and your n is going to be the coefficient of dy, so it is x squared, as you see. So the partial derivative of n with respect to x comes to be 2x. Now, even though you are asked to find these questions, students, you see, you are indirectly asked to find this one, because basically we can solve this directly as it is, but we need to carry out this integration 2 times. One for, you see, this integration and the other for this one. But instead of applying 2 integrations one after the other, we better, you see, have this double integral, because solving this double integral is by far simpler compared to, you see, this one. That's why I'm doing this. Basically, you'll be asked in such a way too, okay? So this is going to be the same as this one. Look, your nx is already obtained 2x, and your my is already x plus 2y, so you need to take the difference between the two. So this makes 2x minus x, and this would be minus 2y dA. And this is done over that bounded region. The integration is done over that bounded region R. Look, here it is, students. This is a graph of the parabola y is equal to x squared passing through the origin, being opened up, as can be shown. And the line, you see, y equals x is, you see this line, the linear one passing through the origin. So where can you have now the bounded region? The bounded region is going to be somewhere over here, as you see, okay? Since the orientation has to be in anti-clockwise direction or counterclockwise direction, you see, you need to move from 0 to 1 first, and then from 1 to 0 back, okay? So point of intersections can be obtained. Look, here we do have one point of intersection at the origin and the other is at 1. This basically can be done by solving these two simultaneously. For instance, y and x are the same, so in place of having y here, you may take x here. X equals x squared comes true when x is either 0 or 1, or you can take x, you can bring this x squared to the left, x can be taken, then 1 minus x equals 0 can come. So you do have 2 options for x to be true. One is either x0 and the other is x to be 1. So based on this, you can find point of intersections at 0, 0 and at x1, y1, right? At x1, y1. So this integral is going to be performed over this region, right, students? So this dA is going to be now written as dy times dx, because this is a vertically simple region. As you see, we can just solve that by using vertical simple region approach. So as can be shown here, our dy dx is written here, but when you see the y extension, here we are having what, students? Here we are having the lower function is the parabola x squared. That's why I wrote here EC underneath, and the upper part is EC y is equal to x. That's why I'm having here x upper. And this integration is going to run along the x-axis from 0 to 1, because everything here, this region lies between 0 and 1, so 0 to 1. Now let's find this integration. So clearly this is the integral from 0 to 1 as you see, and whenever you integrate this respect to y, this comes xy as you see, and minus 2 y squared over 2 actually can come, but 2 cancelled by 2, then y squared can follow. Evaluation is performed from x squared to x as you see, so we need to substitute first x in place of y, and then x squared in place of y, and then we will deduct these two. In doing this, what comes next is this one, students. You do have the negative of the x cubed minus x to the power of 4. Sorry, students, you need to avoid this one. It is written here without careful consideration. And anyway, no problem, just avoid these two, x and x squared. So what is the integral of this x cubed minus x to the power of 4? So simple. This will be x to the power of 4 over 4, and this will be x to the power of 5 over 5, but you have to evaluate 1 in place of x, and finally negative 1 over 20 is going to be obtained. This is how the line integral of this is obtained. Okay, just associating with the Green's theorem, we can have such kind of solution. Look, had you been doing by the given expression alone, you may just undergo two line integrals, because for this particular integral, for this particular curve, for the lower part you do have one integral, and for the upper part you do have another integral, because finding the line integral over a curve, over the curve C, is finding the two line integrals over C1 and C2. So instead of doing that, we better tackle the problem by using Green's theorem as you see. I hope you have understood. And what comes next is question number 10. So you are given with a certain velocity field here, students. This is your velocity field, and at any point x, y, z, the velocity field is given by this expression as can be shown, and you are asked to find a place where the fluid can be divergence free. So in order to know that, what you need to do is you have to look for the divergence of this v, and the divergence of this v has to be equated with 0, because it is here that we can have the case where we don't have either the case where we don't have either sink as well as source. So we have to look for, you see, the place where the divergence of this is going to be 0, because it is here that we have divergence free condition. So the solution goes like this. So now look, the divergence of this velocity field is calculated, and it is directly obtained by taking the partial derivative with respect to x of the first component, which actually is x cubed y z squared, the partial derivative with respect to y of the second component, as you see, x squared y squared z squared, the partial derivative with respect to z of this one, as can be shown, x squared y z cubed. So clearly the partial derivative with respect to x is 3x squared y z squared, right? 3x squared y z squared, and the partial derivative of this with respect to y is 2 comes down to x squared y z squared, and the partial derivative of this with respect to z is 3x squared y z squared. So look, all these three terms are, you see, like terms, so we can operate them. 3 plus 2 makes 5, and 5 with 3 makes 8. 8x squared y z squared. So we need to now observe the case where this can be 0, and clearly it can be noted that at a place where x, either x 0 or y 0 or z 0, this goes to 0, right? And we know that at x 0 we do have yz plane, and at y 0 we do have xz plane, and at z 0 we do have xy plane. So whenever you see the fluid is around the planes, you see the velocity field comes divergence free. That is the idea. Okay, students, I hope you have understood this one. So this comes 0 when either x is 0 or y is 0 or z is 0. So whenever the fluid comes around the planes, the case where divergence free is going to happen. Okay, students, now comes the part 2 of your final exam, and that is about the Laplace, to find Laplace transform of this function, and based on that you are asked to find this integral. So how is this done? So simple. What you need to do is you need to recall the definition for, you see, a Laplace transformation and also properties of Laplace transformation. So if you remember, students, in our class we have studied how you can transform Laplace of a certain function divided by t. So the Laplace of a certain function divided by t, as you see, this is a numerator function divided by t is nothing but it is the integral from s to infinity of the Laplace of this function ds, right? So we have to find the Laplace of this the numerator expression, which actually is 1 over s plus 6 for this particular case, minus 1 over s plus 2 for this one. So as I said, this is the integral from s to infinity of, you see, the Laplace of this is 1 over s plus 6 and minus the Laplace of this one is 1 over s plus 2. This was the property we were having, right, in the Laplace transformation. Now from this you need to recall how you can find the improper integral of this one. So this is going to be the same as this. As you see, b is going to infinity, so here infinity is held by b, as you see. So the limit from s to b as b going to infinity of 1 over s plus 6 minus 1 over s plus 2 ds can come. Now, dear students, we need to find the integral of this one first, and then b and s are going to be evaluated one after the other, provided that this is taken into account. So from this, the following can follow. The limit as b going to infinity of, now dear student, that this is ln s plus 6 and this is ln s plus 2. So we can unite the two by using over. Remember logarithm property. So as you are putting b in place of s, ln of b plus 6 over b plus 2 can come. Then minus comes because of the fundamental property of fundamental theorem of calculus. Then you need to put s in s there, then you do have a minus ln of s plus 6 over s plus 2. So the limit is analyzed on b, so this is nothing for, you see, this limit, because this is treated as a constant one, we don't have b there. So as b goes to infinity, this is going to be ln 1, right? Because take ln out and analyze the limit as b going to infinity of b plus 6 over b plus 2. Okay? Because as b goes to infinity, b plus 6 over b plus 2, both are, you see, positive expressions, no problem. So the exponent they are having for the numerator as well as for the denominator, you see here is 1, number 1. So we can take leading coefficient ratio. Just we are having 1 here, again 1. So 1 divided by 1 is 1. So the limit ln 1 can come. And we know that ln 1 is 0. And we know that ln 1 is 0. 0 minus ln of s plus 6 over s plus 2 can come. And from this, what comes next is this expression, negative ln of s plus 6 over s plus 2 can come. So this is negative, so I can take this as ln of s plus 2 over s plus 6, because I can take the reciprocal of this one, because negative 1 can be taken up. So this is finally ln of s plus 2 over s plus 6. So dear students, what comes now is, you see, the Laplace of this function f of t is the one we are having here, is obtained to be ln of s plus 2 over s plus 6. But the other question that we need to answer is this one. What about the integral from 0 to infinity of e to the power of minus 2t f of t dt? So dear students, if you remember, this is Laplace definition at s2, right? At s2. We already have defined what Laplace of f of t in terms of s. So in order to obtain this one, you see, just a matter of using 2 in place of s, because this is the Laplace of the function f of t at what? At s2. So you simply put 2 here, and then the following can be what? Obtained. Look, the Laplace of f of t is directly this one, because the function we were having at f of t is this. And by definition, the Laplace of this function is this, is a power of minus st times f of t dt, as you see. But here in our question, we're having is a power of minus 2t times f of t dt. But this is already determined as ln of s plus 2 over s plus 6, because the Laplace of this is already obtained from the previous slide. So when you take s to be 2, you are going to have this to be like this. When s is 2 students, this is going to be ln of 1 over 2. Basically, dear student, there is one thing that I would like to add here. Here we are having e the power of minus 2t, okay? Look, in place of s, 2 has to be used. So the integral from 0 to infinity of e the power of minus 2t must be added here, students. It is forgotten, please try to add that here, okay? e the power of minus 2t times e the power of minus 6t minus e the power of minus 2t over t is going to be ln 1 over 2. But we knew that ln 1 over 2 is the same as negative ln what 2. So the Laplace is helpful in order to find integral of this kind. Now what comes next from this is the following one, okay? You are asked to evaluate this integration. As you see, you are asked to evaluate this integration. So this is basically line integral of a scalar function, because of scalar function is xy minus z, and c is the line segment from minus 1, 1, 0 to minus 2, 3, 0, 2. So initial point as well as terminal point is given. So what we need to do to find this integration is we have to know the parametric equation of this line segment, and based on that we can determine, you see, the line integral of this scalar function. So the solution goes like this. The parametric equation of this line is obtained to be this one. What I did here is I took the initial point as it is, minus 1, 1, 0, plus t times, this is a parameter t. Now deduct this one from this, minus 2 minus minus 1, which actually is 3. Minus 2 minus minus 1, which actually is minus 1, right? Minus 1. And 3 minus 1, which actually is 2. And 2 minus 0 is 2. So the initial point minus 1, 1, 0 plus t times minus 1, 2, 2 can be taken. Our t range is from 0 to 1, because when t is 0, the initial point can come. As you see, when t is 0, this goes 0, the initial point can come. And when t is 1, okay, the terminal point, this one can come. So whatever point you may take now between 0 and 1, a point on the line segment can be obtained. So this is a parametric equation, okay? So your r of t now comes to be, look, this one. What I did here is minus 1 plus minus t, it is minus 1 minus t, and 1 plus 2 times t, 1 plus 2t, as you see, 0 plus 2t, it is what? 2t. Once you have this, you need to derive this one, because here in x, y and z expression here, we are going to use this expression of t's, and we know that ds is the norm of the derivative of what? This parametric equation times dt. So we have to find the derivative of this one. What is the derivative of x? It will be minus dt with respect to t. It's minus dt with respect to t, it will be 2 dt, and this one again comes to be 2 dt. So from this, the integral of xy minus z ds is going to be the integral from 0 to 1 of f of r of t. When I say f of r of t, I mean in place of x, y, z here, we're going to consider x of t, y of t, and z of t, and we need to take the norm of the derivative of this parametric vector r of t dt. And then this is 0 to 1 of, we know that this is x times y, so x times y will be minus 1 minus t times 1 plus 2t, as you see, minus, let's say z, so z here is 2t, it's directly taken. Then we have to take the norm of, you see, the norm of the derivative of this one. The derivative of this is minus I, and the derivative of this one is 2j, and the derivative of this one is 2k dt. This is how a scalar function, the line integral of a scalar function is defined. So dear students, know that this is equivalent to this one. You see, in our class, if you remember, we defined the line integral of a scalar function as like this, and based on that, we simply took the parametric equation of the line and substituted, as you see. So the next task is a matter of now evaluating this one. So from this, the norm of this minus I plus 2j plus 2k makes 3, because the square root of 1 plus 4 plus 4 makes radical 9, and that is 3. So integral from 0 to 1 of minus 1 minus t times 1 plus 2t minus 2t can come, and after simplifying this, you will obtain that to be this expression, minus 1 minus 5t minus 2t squared. So integration of this is going to be done one after the other. So you will get this to be minus t minus 5t squared over 2 minus 2t cubed over 3, then we need to put t 1 in place of t. So as you are substituting 1 in place of t, you will obtain this value, and the final output of this now comes to be negative 25 over 2. Thus, when you evaluate this like this, you see, you will obtain the value or the final output to be negative 25 over 2. Now we are asked to find the solution for this particular differential equation. This is basically a first order differential equation, which actually is a Bernoulli's kind. So we have to solve this by using that approach, okay? So if you remember in the class, we called the coefficient of y as p of x. So your p of x is 1 over x, and the coefficient of y squared is x ln x, so call that to be f of x, and the exponent for y is 2, as you see. So your n value is 2. So now your question at hand, dy over dx plus 1 over xy equals x ln x y squared is going to be like this. What I did here is I just divide the whole by y squared. So in dividing the whole by y squared, this is y to the power of minus 2 dy over dx plus, we see as you are dividing this by y squared, 1 over y is going to come, which actually is y to the power of minus 1. No more y squared, so x ln x can come. So now our intention is to change this to linear form, so call this to be v, y to the power of minus 1, you may call it v. So if you let v to be y to the power of minus 1, dv by dx is going to be minus y to the power of 2 dy by dx, which actually is minus 2, okay? Look, as you are bringing this minus 1 down, minus y can come, but as you are subtracting 1, minus y to the power of minus 2 can come. This, please correct this by minus 2, okay? Minus y to the power of minus 2 dy over dx can come. Anyway, this is going to be substituted by dv by dx. Then this is going to be dv by dx, as I told you earlier. This is dv by dx, and this will be negative 1 over x times v equals negative x ln x, because the one we are having here minus is multiple throughout. That's why I'm having here minus minus. So dv by dx is negative 1 over x times v is equal to minus x ln x. So this basically is a linear expression, so we can solve this linear expression by the formula we wrote before. So this is going to be obtained by integrative factor. The integrative factor is e to the power of the negative of p of x dx, but this is your p of x, I mean your negative 1 over x. So take negative 1 over x here. In front we are having minus, so minus minus turns to plus, and this, I mean this will be, okay, is a power of integral of p of a, the coefficient of, okay, the coefficient of v dx, the coefficient of v dx, and the coefficient of v is negative 1 over x. So is a power of negative 1 over x dx is going to be what is that? Is a power of negative ln x. All right, is a power of negative ln x, but that minus can be taken up, and is a power of ln 1 over x, and is a power of ln 1 over x basically is 1 over x. So the integrative factor is 1 over x. So having this means if you multiply this by 1 over x, you see everything changes to exact form, right? It will be an exact differential equation later. So let's multiply this by 1 over x and use grouping technique. So look, I just multiplied this expression by 1 over x. In doing so, 1 over x dv dx minus 1 over x square v, and no more x here when you multiply by 1 over x, and minus ln x can come. So now we can now consider this as, you see, a d by dx of v over x, students. If you carry out the derivative of v over x with respect to x, you will encounter this one, grouping technique, okay? I just grouped this one as v over x. Here I am having minus ln x, as you see. So, dear students, if you multiply both by dx and integrate, you will come across with this one. So v over x comes, and minus integral of ln x dx plus a certain constant follow, and from this v over x minus of integral of ln x dx. For this you need to use integration by part. Need to use u to be ln x and dv to be dx. So using integration by part, we can obtain this to be x ln x minus x. We do have a negative outside plus a certain constant c. we knew what v is. What v is simply 1 over y. So this is going to be 1 over yx, right? And it will be 1 over yx minus x ln x plus c, multiple this by negative. And finally, as you are solving this one, what comes here is just take the reciprocal and try to divide both by x. You will finally obtain the solution to be like this. Okay, so y is 1 over x squared into 1 minus ln x plus xc. This is how you see this Bernoulli's differential equation is solved. And proceeding to the next question, question number 4, we have this one. It says use divergence theorem to evaluate this particular solution, this particular question. So how do you find now the solution for this by using divergence theorem? So for this, what we need to do is like as follows. So using divergence theorem, we do have this one. See, the surface integral is related with the triple integral, as you see. So your function f here is a vector function taken to be this one, as you see. So we need to find the dot product of, this is the del operator with this vector function. This is very important. The nabla or the del operator dot with f must be obtained. But had you been solving this one by using this, it would have been somehow complicated. Okay, so finding this is the same as finding this one, right? So we're now going to answer, you see, this one based on the triple integral. Okay, so we need to find the dot product between these two. So the dot product between these two is obtained by partial derivative with respect to x of the I component for x, partial derivative with respect to y of the y component, as you see, minus 2y squared, and partial derivative with respect to z of the z component, d squared. So the partial derivative of this is 4, and this one is minus 4y, and this is 2z. So this is already determined. Now it comes is, you see, integrating this triple integral over the given surface. So the given solid region D. The given solid region D is a sphere, as you see, a sphere of radius 3. So we need to use spherical coordinate approach. So this is 4. Your y is rho sine phi sine theta, and your z is rho cos phi. So the others are as they are, 4 minus 4 plus 2, all are written here. So your dv is rho square sine phi d rho d phi d theta. This is your dv in the spherical coordinate. So your rho runs from 0 to 3 because radius is 3, as you see, and your phi is from 0 to pi because it's a full sphere. And since against a full sphere, you see, we are going to take theta's range from 0 to 2 pi. So when we simplify this, you will encounter this integration 0 to 2 pi of 0 to pi of, now look here, this is rho square. So this rho square comes here, rho being rho cubed over 3, so 4 over 3 times rho cubed can come for this particular case. Just multiply these 3 terms by rho squared and then integrate that with respect to rho and evaluate from 3 to 0. Students, you will obtain this result to be 36 minus 81 sine squared phi sine theta, 81 over 2 cos phi sine phi, and then the phi and the theta can follow. Again, here we can interchange these two guys because we don't have theta here. If we don't, I know, yeah, we can interchange basically because integrating the first one with respect to theta is simpler, and again this one is simpler, so we can exchange these two. So as you are exchanging these two, d phi and d theta as d theta and d phi, you need to exchange again these two, 0 to pi and 0 to 2 pi. So look, after exchanging, we can have the integral 0 to 2 pi, but now here you see 2 pi minus 0 is 2 pi, 2 pi times 36, 72 pi. So this integral of sine theta is minus cos theta, minus makes plus. But you see what happens here is, as you are substituting pi, cos pi is -1, and this one is cos 0, it will be 1 minus 1 makes -2, so multiplying 2 by 81, it will be 162 sine squared phi plus. Here again, you see, after evaluation, you will obtain this to be 81 pi cos phi sine phi d phi, because we don't have here theta, so it will be 2 pi, you see, integral of 2 pi, integral of, what is that, integral of, integral of pi can come, and yeah, 2 is cancelled by 2, 2 pi can come, and 2 is cancelled by 2, and then we can have 81 pi cos phi sin phi d phi. Anyway, just try to find this integration and evaluate the integral from 0 to pi again. And as you see doing this, what comes here is the following one: 72 pi squared minus 162. So I can now undergo integration for each of these one by one, and you will finally obtain these to be, as can be shown, 72 pi squared minus 81 pi. Now, after this, what comes next is, you see, question number 5, the last one, and it says use Stokes theorem to evaluate this under a triangle ABC with vertices A, B, C as it has been given. So what we need to do is, the given vector is, you see, x plus yi plus 2x minus zj plus y plus zk. Okay, it's already available here. So what comes next is, look, we need to use Stokes theorem. Stokes theorem associates this one with line integral with surface integral, and we need to take the curl of f. The curl of f is the cross product of the del operator of the nabla operator with f, so have ijk plus minus plus, and this nabla operator or del operator is partial respect to z, and your components are of f are written x plus y to x minus zy plus z, directly obtained from this one, as you see. So in doing so, we can find this answer to be 2i plus k. So the curl of f is already obtained. So Stokes theorem associates, okay, this line integral with surface integral. So the triangle is 3x plus 2y plus z minus 6 equals 0. Try to think of how you can find the equation of a plane provided that 3 points are lying on it. So you will finally come across with this expression. So your z is going to be your f of xy, the surface, just solve for z. You will have this expression. So your m is x plus y, the i component, the j component is n, and your, you see, k component y plus z is taken as it is as p. So the partial derivative of this respect to x is minus 3. The partial derivative of the plane with respect to y is minus 2. So using this Stokes theorem that associates the line integral of a vector function with the surface integral of the curl of the function, we can obtain, as you see, this expression. We have read this in our classroom, students, if you remember, since we are having a positive orientation, because as you are moving from A to B and from B to C, you are moving in counterclockwise direction. You can just have these 3 vertices on 3 x, y, z axis and trace it. You will obtain, you see, the orientation to be upward. That's why I'm taking this. So everything is known now. M, fx, n, fy, p all are known. So this integration is done now with respect to, you see, the region R. So this is going to come. We knew what m and fx, n, fy, and p are directly taken from these expressions. So we can have this one. After simplification, one can obtain this to be 10x plus 6y minus 6. Okay, just simplify this expression. We'll finally come across with this. But now your dA is dy times dx. So, but in place of y, we can take, okay, we can take y to be this expression, as you see. And this is obtained basically making z 0, because you are on the xy plane. If z is 0 and solve for y, you will come across with this. And then you're having y range from 0 to this one. Your y range is from 0 to minus 3 over 2x plus 3. And dy dx can come. So everything is given in terms of x. So after simplifying this, you can obtain this expression, and a single integral with 1d is going to come. And after evaluating this expression, okay, after finding the integral of this and evaluating 2 and 0 one after the other, you finally come across with this result, 1663 over 287. So Stokes theorem associates line integral with surface integral. Had you been solving, for instance, this for three sides of the triangle, it would have been very complicated because you are expected to integrate 3 times for these 3 sides of the triangle. But instead of doing that, we better tackle by using this Stokes theorem. We did simply this step and find the result.